Yes, now we are all good with the recording. So we have some little slides prepared to explain better how the performance of the rocket will be and like some general info. So I'm going to start sharing the screen to show you that.
Great, sounds good. Thank you.
So can you all see the screen, right?
I can
Yes.
see it.
Okay, perfect. So this is some a picture of us as a team. There are some people missing there because it's hard to align the schedules of a lot of people, but that's us, and that's our rocket that we are with. This is a little exploded view of the rocket. It's basically what you can see here on the table. That we will go further into that a little bit later on the review. Here we have like some basic rocket information. We have a COTS motor, specifically an N3300R from IREC. We have one stage. Our vehicle length is 3.64 meters. We have an airframe diameter of 17.4 centimeters. And we have 4 fins and yeah. This is a basic open rocket overview of our design. We have a stability of 2.55, 53, I'm sorry. And yeah, an expected apogee of about 3,113 meters and an expected max velocity of 0.81 Mach. We have a lift to thrust weight ratio just at a liftoff of 6.91 and a rail departure velocity of 26.92.
Yeah, so in general, we did a little bit of analysis using OpenRocket and RocketPy in order to determine which way was better to establish our predicted flight data, right? So in general terms, our predicted flight data, as Melissa said, we are currently on a target apogee of approximately 10,000 and 4,000 feet. And as you can see on the slides, we have this flight trajectory, and also we did like a general analysis of what of which was our recovery radius in order to determine all the parameters that we need to do at the moment of the recovery. And the maximum recovery radius that we could determine was 1.8 kilometers.
Is that with a nominal flight, or
No,
is that
that is like with an nominal flight. We are doing that. We did this analysis using a variation with the wind speed, the wind direction, and the rail direction. So all this analysis was like an iterative analysis in order to determine which is the largest radius that we could have at the moment of the launch. So yeah, this predicted radius, this maximum recovery radius, is with the worst case, having winds up to, if I'm wrong, 10 meters per second, with a direction that doesn't help us in order to have a great apogee. And yeah, that is like the worst case scenario. But as you can see on the graph, there is a lot like of points that is the analysis that we done that are very near to the launch site.
so? My question was more about nominal flight in terms of recovery ejection charges. If for some reason your main parachute comes out at apogee, is that included in this analysis?
This is in this case, this is just a nominal scenario. Then this is
Okay.
just that the drug parachute ejects at apogee and the main parachute at 450 meters above ground.
All nominal.
And I would like to add that this is considering a minimum rod angle of 82 degrees, according to ESRA. So this is the maximum we expect in a nominal scenario only.
Cool.
Okay, so for that general information, that's like all that we have. I don't know, Sierra, if you maybe have like a specific order where you would like to start the review, or like, yeah, where do we start showing you our rocket?
Yes, yes. So could you start off by showing me your nose cone, just kind of giving me your general overview of it, material, and kind of showing it to me, showing how long your coupler and everything is, your shoulder.
Okay, so this is, can you
Let
see like the
me,
mobile camera? Or like we stop your screen, like, just to check that.
I expanded your camera, so you don't need to.
Okay, like it's like the thing is that we have two cameras, like one fixed, that is the one that I'm pointing at right now, and a mobile camera that is like the one I'm pointing at.
Oh,
Like,
I see. You have another
like
camera.
which one? Yeah.
Oh, yeah, I see. Okay, cool.
So, permítele.
Yeah, that's good.
So this is our nose cone. It's made from fiberglass. Our coupler length is a little bit more than one caliber. It's 18 centimeters long approximately. And what you can see here is like kind of a polyester hoodie that we just put in there, like just for geometric purpose.
You're kind of quiet. Could you speak into the microphone?
Oh, here. So, do I repeat like everything, or just?
I could hear
Okay.
enough just where you were just talking about
Oh, okay.
what you were looking at. Yeah.
Perfect. I'm sorry. So yeah, that's like we have, and for the tip we have metal section. We wanted to have like a multi-purpose components. So this, besides being the tip of our nose cone, it is also the point of attachment of the eye bolt for the shock cord. So yeah, we have something to explain about this, because this is like threaded. For the flight, it's going to be like permanently glued. And for this, we are going to implement a specific system that my peer is going to explain right now. And yeah, like that.
Okay. In past meetings, we identified some problems with the anchorage between these three pieces, the three components. That is the tip, metal tip, this anchorage, and the eyeball section. That is this. How Melissa says, this component or this assemble has three, okay, a multiple purpose in the rocket. For example, the main and when we identify the problem is that this section place has a bulkhead, yeah? So with the eyeball, in the ejection, in the recovery stage, the shock cord pulls the eyeball and turns around the axial direction. So to reduce this risk, we are going to make a pull hole in this section in order to block the rotation of the eye bolt. And in the tip section, we are going to assemble to the nose cone, to the fiberglass nose cone or the body nose cone. And we are going to realize a permanent bonding with a special epoxy adhesive, that is this that you see here. That is the same that we are going to use that we use it to the first stage of the fin's anchorage.
Was it structural epoxy? Is that what you're using?
Yeah. Yeah, all this epoxy that we're using is certified as an aeronautical epoxy. We did all the research with the technical specification of these epoxy adhesives, and also the team did all the calculations in order to determine if this epoxy was adequate to ensure that it's strength enough for all the forces that are going to experience the rocket. So yeah, in general terms, this epoxy is certified to be used in this rocket. We did all the calculations to establish that we could use this epoxy adhesive. And yeah, as an additional, we are going to use like this spin cutter, like a mechanical bond, a mechanical blockage between the nose cone this because the nose tip section and the eyeball in order to block this radial movement that could have the eyeball.
Yeah, how Dylan says, we done all the research, all the study to determine how kind of epoxy adhesive we are going to realize. This is in our technical report.
Yeah. We'll continue with the.
Okay.
Something else.
Uh,
I'm sorry, they have a question.
And then I know that you guys aren't completely finished. It looks like you still need to paint. I'm not sure what else you might need to do. But do you have your plan for where you're going to put your shear pins throughout your rocket?
Yes, we do. I want to add like a little data about the
Yeah,
the
go
nose
ahead.
cone, and that is the the rocket will eject in two sections, from the nose cone and from the motor down. I'm going to talk a little bit about the nose cone. So here you can see the holes on the shear pins. The nose cone will go
Okay,
like
great.
this. There are 4 shear pins, and also the recovery guys did this ring. This other ring we go attached to, like you can see like those little holes.
Mm-hmm.
And that it's to avoid the main parachute to get like stuck on the nose cone during the ejection.
What size screws are those?
And
For both the bulkhead and the shear pin, please.
Yeah, we are using the Sharpies. We're using 4 M4 screws. Also, with calculations needed, the metric size is M4. The M4.
Okay, M4.
Yeah, we are using 4 for both zones of ejection: the nose cone section and the bottom, the motor section. We are using 4 Sharpies for each ejection event.
Okay, 4 shear pins for each. And have you completed your ejection testing yet?
Yeah, we are currently working, and you can show maybe we plan to do like a little bit further in the presentation, but yeah, we already done some ejection testing. For example, this is the nose cone ejection testing, and all the tests have been going well. And if you like to talk about the deployment charge, or maybe later, and we continue like from the tip to the bottom of the rocket.
We'll keep going from the tip to the bottom of the rocket.
Okay, so yeah, anything more questions related with this nose cone section and the Sharpins, or everything is clear?
Okay, so you are attaching your parachute to that nose cone tip. Is the parachute in the nose cone? Is there anything else around this area?
No, so currently we are working with this configuration that you can see right here, as Melissa explained. We are working like with this, we call it like the pressurization bulkhead. This allows us to to block the movement of the parachute in order that it is not going to be like stuck inside the nose cone. So
I'm not sure if your other camera is on.
Sorry?
I don't know if your other oh, there it is. Yeah, I see it now. Okay.
The camera that's your main camera is all of your backs.
Yeah.
There you go. Now you've got
Yeah, that's
the
good.
main
That's
camera.
good.
Yeah, so currently, yeah, as I was saying, the main parachute is going to be fitted inside of the nose cone, but its pressurization bulkhead that we designed prevents the parachute to get stuck inside the nose cone. Yeah. So my partner here, David, is going to explain a little bit further of this parachute configuration.
Regarding a little bit more information about the shock cord, we have in total 3 shock cords. This first one is obviously for the main parachute. It is rated for 8,600 pounds. So it is in fact pretty strong, pretty way high than the forces we expect. Attached to it, it's our main parachute. This is a CUTS parachute from Sky Angle. In fact, it's pretty heavy duty parachute because of the thickness of this fabric. And in fact, it was the best CUTS parachute we could find in the market. So with this parachute, we're expecting a descent rate of 4.38 meters per second, which is pretty low, but it is a descent rate that we actually need. And I will explain that later, because in general, it has to do with our payload. Our payload requires a low descent rate. So that's why we require a big parachute. This is from Sky Angle. I don't know if you identify them. They're pretty good.
What is that parachute size?
In terms of diameter, it has approximately 4 meters in diameter.
4 meter in diameter. And this is your main?
Yeah, this is our main.
Okay. And
Cool.
is your drogue lower than when you start showing the rest of the rocket?
Yeah, so before going to the drogue, I have to make the note. We have a pilot parachute, which will help to extract this one from the deployment bag.
Yeah, okay.
Because on a recovery diagram or the recovery process, the drogue will be above the main when trying to deploy the main parachute. So we actually expect that this pilot parachute help us to take the main and place it in an upper position than the drogue parachute. I can show that to you in that diagram. If you could share.
We're in the process of sharing the screen
please.
to show the diagram.
This is just like how we expect. It is, of course, an ideal case, but you can see in this diagram that the nose cone, where the main parachute is, oh no, this ain't the diagram. The drogue one, please. Here. You can see that the drogue parachute is placed above the nose cone. So we expect that the pilot parachute helps to extract the main parachute and place it above the drogue, sorry.
Okay, and how long is that shock cord?
This shock cord for the main section is 35 feet in length.
Okay.
And we also did an assumption to define this length that was like I am ejecting my nose cone downwards, right? So we cannot allow that the full length of this shock cord that's going to unfold hits the engine section. So this shock cord should not collide or make the nose cone collide with the other section of the rocket when deploying the main parachute. And that's why we have 35 feet main shortcut.
Yeah, and how long is your rocket in feet?
When deployed or just
Just all together.
We're doing the conversion.
yeah, we didn't the conversion.
Okay, thanks.
Like in meters.
Yeah. Mhm. 11.9 feet.
Okay, great.
Yes. And yeah, that's regarding these parachutes. Now, if we talk about the drogue parachute, it is also from Sky Angle, which is a pretty small parachute. And it allows us to descend at a fast descent rate because we actually, in all the design process, wanted to obtain a minimum horizontal drift. So this parachute descends at 38 meters per second.
We're going to tell you now how much that is in
In feet.
per second.
It is slightly below the ESRA limit, which is 40 meters per second.
It's 124 feet per second.
Okay, thank you.
And just the final two notes about parachutes. Both of them have deployment bags, which is a fire protection measure we decided to take. And both of them are also cuts from 3D shoots. And each one of them also has a swivel link as a requirement of ESRA. And they're capable of supporting the forces the parachutes will experience. So we're covered regarding that matter. And that will be everything related to parachutes.
And what's the diameter of your drogue?
It is around 90 centimeters. I think it is 86 centimeters.
We're going to tell you how much is that in feet in a second. 2.82 feet in diameter.
Yeah. And finally, regarding the drogue shock cord, it is larger than the main shock cord. It has 65 feet in length, just because our payload requires that the fuselage that it's below him, it's very, very, very far away from him, because this payload takes wind speed data. So we really needed like the less disturbances in the air so that this payload can take accurate data. So that's why we decided to have this pretty large shock cord, and it has the same load rate than the other one, and that's it. As an additional thing, our CubeSat goes attached to the shock cord. It will not deploy and be independent of the rocket. It will be always attached to it by the shock cord. And this will be done through a Y cord, which in fact is here. This Y cord is attached to two opposite corners of the CubeSat. And as an additional safety measure, the drogue shock cord also passes through one side. Could you help me, please? We have two shock cords passing through the CubeSat. The main one, it's of course the drogue one, which just connects the fuselage, the rocket itself. And the Y cord is just an additional shock cord that just helps to maintain this CubeSat in place. But as an additional safety measure, the CubeSat has like guides or rail guides that just allow this shock cord to be placed alongside it. so that there will be no relative movement of the CubeSat with respect to the shock cord, because we actually want it as still as possible. So that's in general how we attach the CubeSat during flight.
So you're attaching your CubeSat via shock cord.
Yeah.
It's important to
So-
know that this structure right here is 3D printed, but this is not the final one. The final one will be in metal, in aluminum.
Okay, so this is 3D printed, but the final will be in aluminum. Okay, I was getting a little nervous. Okay. Okay, 3D printed prototype. So it's not bolting in any way, it's just attaching via shock cord to
Yeah.
the airframe.
Yeah.
Does it come outside of the airframe when it flies?
Yeah.
Yeah. It
Yeah.
will be exposed to the first year.
It'll be exposed, but it's not going to fall it doesn't fall
No,
independently
by
of the
itself,
rocket.
no.
No,
Yeah.
it is
But it
always
does
attached.
get ejected from the tube.
Yeah.
So it's ejected and then you just expect it to fall just kind of dangling from the rocket.
It looks like it. That's what that Y harness is. So
Yeah.
it's still attached.
Yeah.
It's attached to the harness, but it will be outside of the tube
Yeah, it will be falling outside the rocket.
so that it can
And-
collect data, right? It's like an atmospheric thing, right?
Yeah.
Yeah.
Are you attaching to eye bolts on the payload, or what do you have to hook onto?
As this structure will be in aluminum, each loop of the Y cord is directly assembled into the CubeSat. So as you can see, these columns now.
Okay, so you're
Beams.
bolting.
These beams
Yeah.
can be disassembled. So what we will do is to remove these beams, install the shock cord in its respective corner, and after that, assemble the beams.
So are they going to be rounded, those beams?
Yeah, they will be rounded, and we will place like a soft surface, for example, a plastic or some.
Tape or so you can use duct tape.
Yeah, exactly. Just to
Okay.
avoid the corners of the aluminum, because
Gotcha.
in fact they will be sharp, and these shock cords do not behave very well with shear force. So we want to place protection in these attachment points.
So have you done any calculations or any FEA analysis on the effects of the shock cord on this payload frame?
Yeah. Yeah.
Okay, so here we have a payload team member that is going to explain that to you.
Hi, my name is Matter, and I'm the lead of the structure team of the CubeSat. I don't know, ¿puedo compartir en el Zoom?
Sí.
Please. I'm going to share you my screen with the CAD of the CubeSat, because in the 3D printed prototype, you can see it pretty well. So I don't know if you can see my screen.
Yes, we can.
Well, and this is the anemometer portion of the CubeSat where we want to measure the velocities of the wind for directions, and that's why we have like a central column where all the pilot tubes are attached. Then we have the two PCBs, and right in the center we have like all the core of the CubeSat. We have here the batteries. Then we have the three bulbs for the system of atmospheric sample collection. Here we have, well, the name of the CubeSat Luna, And inside we have the air pump of the sample collection system. Here you can see that the valves allow the samples to go to the bars, the sample bars of the QSAT where the samples are going to be stored. And well, here we have the second PCB that is more related to the IMU, and the other things. And here you can see the assembly with the shock. And después hay más. Si quieren van diciendo otra cosa, mientras sería bueno mostrar.
But yeah, we did like the analysis is short, is loading, but yeah, we did all the calculations and with finite element analysis in order to determine that this structure is going to handle well all the forces. We did two approaches in order to calculate the forces. First, the forces of ejection related with the piston impacting the ejection zone and the forces that the parachute are going to have at the moment of the opening. So yeah, we did all these calculations of the forces. All are like explained very well in the final report. And we did all these calculations in order to do analysis of all the structural components in the rocket, not only the CubeSat that we are waiting to load the analysis, but also to do another analysis of another structural components such as the eyeballs, the bulkheads, and the screws that we are using. So yeah, as conclusion, this structure is going to handle very well the forces that we are expecting to have at the moment of the ejection and at the moment of the parachute opening.
So why did you choose to attach the shock cord to those corners as opposed to adding eye bolts?
Because we wanted like to be the simplified way to attach this CubeSat to the airframe and in this case to the shock cord. And we didn't want it to add additional components to the CubeSat that could damage the data acquisition that we are wanting to have. Because as my partner said, this CubeSat wants like to have some atmospherical data related with the wind and with the contamination particles that are located in the atmosphere. So if we added some eyeballs, for example, after some analysis, we found out that these eyeballs could damage the data acquisition principle for the pitot tubes and also for the bags that are made to collect all the samples from the atmospheric air. So yeah, that is the primary reason that we didn't want to add like these eyeballs, because this could damage all this data acquisition that we wanted to do. And this is very like sensible data. Let's call it like that, because it's data that with the smallest turbulence or with the smallest effect could damage the analysis and all the project that our payload team is developing. Yeah. And as you can see on the screen, there is the analysis that the team done in order to determine if this structure will handle very well the forces. And yeah, we are very sure that the structure will resist the shock curve and the opening forces. Yeah.
I have to say here that the scale of the deformation in the simulation, it's kind of in height, but it's, as you can see here in the results, they are in meters. So the maximum deformation that we could have in the simulation is like 0.5 millimeters. So it's so short. Also, the force that we applied in the simulation was too high from the maximum values that we calculated.
So to give you the number in inches.
It's 0.02 inches. Sorry.
Inches. Oh, goodness. And about the stresses that we are going to have in this situation that is above the nominal, all the stresses that the structure will receive are within the limits of the structure, so we are okay about it.
So, a few questions. What is the force that you applied in this FEA, and where did you get it from?
We applied a force of, I don't know how it's in fact.
Yeah.
You can say newtons, that's fine.
Okay. So, as Dylan said earlier, there are two types of forces or loads we expect during recovery. The first one, it's just a snap due to the tension of taking the shock cord and extended it all its length. So due to that action at a low time, there will be like a high force due to the tension between rocket sections. That was named by us as a snap force. And this tension is the one that we are applying to the fee analysis. I will get you the value right after I explain you the other force, which in fact is higher than this one. The other force is the opening force of the parachute, which is just an effect of inflating the parachute at a certain time. And as a result, we expect that the load applied in this analysis is 4,700 newtons, which is like 4,700 newtons. And this is the value that was applied to each point of this CubeSat in terms of vertical force. I don't know if that is clear.
Okay. And then did you analyze the bolts that you have in those locations at all?
Bolts of this CubeSat.
Yes, like if the bolts would shear under that force.
Yeah, we're still making the analysis, but yes, we are not on it.
Yeah, it's still in progress. The analysis in terms of deformation, bolts, stresses for the payload. We have
Okay, yeah,
values,
just
but
make sure to
it's still in
check the
process.
bolts,
Okay.
since that would be sort of your weakest link in this frame. How wide are your columns?
Wide, like this?
Like, yeah, like height, width, depth, whatever.
It is around 5 millimeters.
It's about
10. 10.
it's about half an inch more, approximately.
Okay, half an inch by
Okay.
half an inch. Are they square?
Sorry, what was the question?
Are they square? Is it half an inch by half an inch?
Are they square bars? Are you guys
Yeah.
using the-
Yeah, they're square.
Yeah.
Okay.
I don't know if we like keep talking about like the payload or like going into where we left and go down. I don't know. You tell us and we do.
Well, let's just stick with the payload for now since we're talking about that. Your materials, you said it will be made out of aluminum in the final product. This is just a prototype, correct?
That is correct.
What batteries are you using in this payload?
What
Yeah.
pattern?
What batteries?
Batteries.
21,700. I don't.
Okay. And what type of battery is that?
There are lithium batteries. Lithium, no lipo in lithium. There are the Li-ion here. It can be it's easier because of the pronunciation, but
Yeah, yeah. And then what kind of casing are you holding those in?
For the moment, it's in the prototype, it's a 3D printed casing of the batteries, but we
this
are
is
going
the
to use
avionics
something
rack.
like that.
However, it's pretty similar to this one. Is where the commercial one, where this battery is just put right
Okay.
there. So it's basically a similar one to this, where the batteries are going to be on the structure of the payload.
Where are you getting the battery holder from?
In the, I got to share you again. Oh, here. What this is what you see here, these bots is a product cage that we put in the QSAT because the electromagnetic fields of the batteries and the bulbs and also the pump were going to affect the measures and the functioning of the PCB.
Right, but my question was, where are you buying the box from? Like Amazon? No, not that part, the battery box.
We bought it in here in
Colombia.
Colombia. Yeah, it's an energy place in El Carmen.
Okay.
So you're just using a commercial off-the-shelf battery case?
Yeah.
Are you enclosing it in any way?
I think it's protected by they're saying that it's going to slide into that little slot there.
We can
Yeah, but what about the one in the avionics bay?
Oh, okay. So in the avionics, the avionics is going to be right here. And it's gonna be like enclosed on the fuselage, and also they're going to be zip tied.
They're gonna be zip tied to the structure, basically.
Yeah, so for the avionics bay battery holder, is this one as you can see. We're gonna use zip ties at these points and at this point back, and we're gonna insert it as well with tape to make sure like the batteries don't come loose due to the forces it's gonna experience. The holder is gonna be screwed down to the base. This is gonna go this way, so as per ESRA requirements, the holder needs to be on the bottom. So we have that, and yeah, that's how we're gonna set up the battery holder for the avionics. We have also this one here for the SRAT. This one is for the camera that we have on top for the avionics.
And your avionics bay is made of wood for the final product?
Yeah, it will have like these 3 plates, specifically this and this. We have also a couple layers of fiberglass to reinforce it. And also the holes are not made yet, but the avionics bay will go exactly at this point. It will have some metallic thread inserts, 4, like at 90-degree intervals here and here. And they're going to be screwed on the fuselage. Maybe go like right here.
Okay, so you're saying that you're screwing this in from the exterior of the rocket.
Yes, that is correct.
Do you have anything to maintain alignment?
Yeah. Like we have these structural rods, and we also will put these nuts here and here, here and here to keep them from moving.
I kind of mean, so when you put the avionics bay into the rocket, how do you make sure that you put it in the same way every time so that you bolt correctly?
Oh, well, so basically one thing particular about these avionics is that they are like kind of intertwined, let's say like that, with the ejection bulkhead. Like they're not the same piece, but it will go like this. So they have to be exactly on the same position for these CO2 cartridges to go in perfectly.
Okay.
Basically, they're like that. like this, and there's also another ejection bulkhead right on this side. It's like mirror, exactly this same component, but on this side.
Okay, but there's no ejection happening towards it. It's all outside
No.
of it,
Yeah.
away.
It will
Okay.
stay like, actually it's like separated from the ejection gases and all this stuff. It's like just there.
Yeah, we are working like with separate events and separate like parts components, because we didn't want to integrate all these ejection bulkheads with the avionics, because all the forces that we talked about you that we talked with you, we wanted like to do a separate integration. But as Melissa said, yeah, these cartridges of CO2 are going to be like a way that we can align this avionics section with the rest of the components of the rocket. So if you would like to me to explain like the bulkheads of ejection, or maybe if you have anything more question related with this avionics section.
Yeah, so do you expect to see any force from your ejection systems on your avionics bay?
No. We are not
Okay.
expecting to like transmit any force into this avionics section, because as I said, these ejection bulkheads, the other one like that is placed here, are completely independent, structurally speaking, of
Okay.
the avionics section. Yeah.
And they have
Okay, they just
eyeballs.
sit around each other, basically.
Yeah.
Yeah.
Okay, that's good.
Also, yeah, like the avionics is going to go screwed on the fuselage, like it holds it.
Okay, so that's also screwed through the body tube. And
Yeah.
how big are those screws?
They are M4, I don't know, M4
Okay.
measurement.
That's fine.
Yeah. Also for the cameras, you can see that we have like a camera bay.
Mhm.
We haven't done like the whole yet, but this is like how it's going to work. The camera will go outside of the fuselage on a little enclosure. Oh, yeah. There's going to be like a little enclosure for the camera on the outside of the rocket. So we have like, we put in the avionics rack, we put the camera right on the casing, and the camera is, let me put this right here, and the camera is screwed on the sides. Also, yeah, like we will do the hole in the fuselage, and we will do a reinforcement of fiberglass around the rocket for, yeah, given that it's going to be like a pretty big hole.
So how are you pulling the camera into that shroud?
So, yeah, that's on the integration process. So basically what's going to happen is that when we insert the avionics bay on the fuselage, this plate will not be assembled. So like we insert the avionics bay, we pull the camera out like right there, we screw on the camera, and then we put the plate. That's
Okay,
like the
and
integration process.
you can reach that with your tools?
Yeah, we can.
Okay.
It's like the fuselage is not that long, so we can easily put like a hand inside of it and reach whichever we need to.
Okay.
Yeah, so maybe if everything is clear with the avionics section, as Melissa said, yeah, talking about the integration, we are going to, like, this section is one of the primary integrated zones that we are working on. So we expect to do the integration of this fuselage apart. So we can reach, for example, for this type of plates, it can be easily reached from one side of the fuselage. So everything is clear, or maybe you have more question about it.
Have you done any analysis of the effects of the camera shroud on your rocket?
Que sí, hemos hecho algo así.
Yeah, like a little aerodynamic simulation was done, and like it obviously adds drag to the rocket, but it's not that high. Like it can be, ¿cómo se dice? Neglected.
Okay.
And also, this is not aligned with the pins. Important.
Okay. So did you factor that into your simulations when you're predicting your apogee?
Yeah.
Okay, good. Okay, let me make sure that that's all set. Oh, yes. So while we're at the avionics bay, what electronics are you using?
Hello. So let's go through all components in the avionics. We're more interested about the commercial of the shelf avionics. Here behind,
Yes.
they have the Blue Raven, and in this side, we will have the RRC3 Plus computer that hasn't arrived yet. Those are the CUTS altimeters, and we are also mounting a student research and development board. Looking forward to collect data, but mainly these two commercial computers and also well, the live stream video camera. Yeah, sorry. I also forgot to mention the GPS featherweight GPS tracker. It's gonna be here. Yeah, thank you. In the floor of the avionics rack. And on the other side, we have the batteries for each component. This one is for the SRAT. The lithium-ion batteries are for the SRAT computer. Yeah, so my friends are sharing the screen right now. You can see the wiring diagram for the Blue Raven CUTS computer. Okay, well, they changed this. That diagram is for the RC3 Plus wiring diagram. As you can see, both CUTS are using 9 volts alkaline batteries, and the featherweight GPS tracker is using the manufacturer-provided LiPo battery with no modifications. And we're using MissileWorks screw switches, as you can see one of those on the other side here, to both, each CUTS computer has 2 of these switches, one for turning on the computer, another one to energize the pyrotechnic chargers. That's all. If you have any question.
Yes, so that looks good. Have you guys planned out your vent holes yet in this area?
Yes, we have.
Yeah, basically, we have some static ports around this section where the avionics will go. ¿Me puede recordar qué tamaño son? Okay. They are 0.2 inches. Son cuatro, no? There are 4 of them, like around this fuselage. That for the static ports.
Also, you can see that the CUTS computers are on the other side. They're opposite to the cartridges, CO2 cartridges, as they freeze when they activate. So they're on the other side, so they don't mess with the barometer readings or anything with the CUTS computers.
Okay, and then that's where your switches are mounting, those little brackets.
Yeah, that's where this kind of switches will go.
Okay.
We have
Okay,
just
so
one
then
installed,
they'll
but
just
like there are
line up
several of
with
them.
holes.
I'm sorry, could you repeat?
They'll line up with holes in the rocket.
Yes. The holes are just the size to put the screwdriver in. Thank you. But they're not bigger than that, and the screw doesn't come out from the rocket.
Okay. Okay, and then when you were determining your vent holes, how did you calculate that?
So basically, we use like the standard formula for calculating the static ports. I don't have them with me right now, but they are clearly explained on the technical report.
Okay. Okay.
Well, another integration thing that we could mention is that the avionics rack enters by himself, like as Melissa explained earlier, to put the camera in place, and cables are gonna come out from both sides of the avionics rack. These are pretty long cables, and they're gonna go to the bulkhead. In the bulkhead, we're gonna have lever connectors. So the last thing that we integrate in the whole rocket, aside from the motor, are the energetic chargers. So the energetic chargers are not directly connected to the rack, but they're connected to the bulkhead. So they are the last thing to integrate.
Okay, and you said there are wires going throughout the rocket then?
No, they're just in this side. They're coming from the they're coming from this hole,
Okay, okay, I
and they're
see.
to the bulkhead, and there's a
Okay, so
connector
it
in the
is
bulkhead.
all self-contained within the
Yes,
avionics.
this
Okay,
whole section is self-contained.
okay.
I was searching the information. For answer your question about the diameter of the hose to the static pressure ports, we realized calculus taking into account the volume of the avionics bay and complemented. Okay, this calculus was made from NACA's web information that we took from. Yes.
Yeah.
So in complement with that, we done a research of the state of the art of the how all the teams in the past done these holes in the fuselage for the avionics bay. So this was for the objective to verify the information and verify the calculus from NACA's web.
Okay.
Okay, in complement, I want to say that in the avionics bay, the structure, all the structure, for example, the wood bulkheads are going to be reinforced with fiberglass layers, and the black structures that you see, these two, with the same reinforcement, with fiberglass layers.
Then kind of shifting gears, your airframe body tubes, what are the thicknesses of your walls?
The thickness of the walls are 3 millimeters. Please, someone tell me how much is that in inches to tell Sierra. Well, you can see here that 3 millimeters. The team members did a really great job into analyzing all the forces. 0.12 inches. Yeah, that will be like the thickness of the body tubes. The team they really did a great job into analyzing all the forces that the rocket will endure. Also, we did material tests of the fiberglass. They're made from fiberglass in order to verify the material properties and to calculate an adequate thickness. We have a safety factor of 3.
Great.
Yeah, that's it basically.
Yeah. For
And then I
this,
know you haven't painted yet, but you have plans to paint before you leave?
Yes, we plan on finishing the holes that we need on this section and start painting. We plan on taking everything ready for the competition.
Okay, great, great. And then you'll have your team name, your frequency, your center of gravity, center of pressure, all that good stuff on your rocket.
Of course, they will
Great.
be there.
Great. And make sure you put one of your phone numbers on the rocket as well. That is very helpful if you lose it.
Okay, perfectly. That's a really great tip. We will apply it.
You'll be international phone number, email address too.
Yeah, yeah.
Okay, perfect. We will take that. Yeah, I don't know what else
Okay,
we
great.
can. You want to know about the fuselages? Oh, also, like just to say, the screws are M4 metric screws, grade M6. I'm sorry. For the bulkheads, they're M6, and for this coupler, they are M4. They are a grade 10.9, so they are like stronger than your regular bolts.
Okay.
Are they steel? Are they just hardened steel, or are they stainless steel? What are they?
I think that they're hardened steel.
Okay.
Yeah, like the grade it's related to that 10.9 grade.
We selected a general fasteners, general screws in all the rocket with a selection matrix, and for example, the anchors with all the rocket structures are with a metric size M4, 10, 10.9 grade. That
That's
is
a hardness. Yeah.
Yeah.
So they're steel at 10.9 hardness.
that is it. It's a standard. And for the bulkheads case, we have an M6 metric size. Do the objective to increment its safety factor because of this section are going to support the higher forces in the rocket. So, for example, in the M6 fasteners, we have a safe factor of 8, and in the M4 case, we have a safe factor of 4.
Okay. Are they tapered? Are the heads of the screws tapered?
They're horizontal.
Countersunks, yeah.
Countersink. Yeah. Okay. Yeah.
Okay, they're countersink, and are you countersinking into the body tube?
Yep.
Okay.
Like here, some holes like the screw.
Okay. Yeah, I'll trust you. It's kind of hard to see on camera.
Yeah, you can see. I can see it.
Oh, but you can see like here we have like the screws on, and you can see that they lay flat.
Yeah,
the
yeah.
airframe surface.
All of these were with the objective of keep what do you
Yeah,
a smooth surface in all the rocket.
Yeah,
Yeah.
to minimize drag as much as possible.
Okay, great. Great. And then I saw, of course, your eye bolt that's a part of your nose cone tip. Where are your other eye bolts and how are they connecting?
Yeah, well, in general terms, we have another 3 eyeballs. The one that is located on the nose cone that we talked about it, later was the eyeball with the pink color, right? The other eyeballs that we're working on are the eyeballs that are located on these ejection bulkheads. These eyeballs are 9.6. How can I say this? 960. So yeah, 960. As you can see, here is the reference. These are steel eyeballs. These eyeballs are going to be attached to these ejection bulkheads from this fuselage section, and on the motor section, we have another bulkhead of recovery that is going to be located something like here. Yeah, right. As you can see, here is one of the bulkheads that is already installed without the systems, as in order that you can see better how is the organization of these ejection bulkheads onto the rocket. These eyeballs are going to be attached using a lock washer, a lock nut, and also this bulkhead is threaded on the inside in this point. This bulkhead is also threaded. So yeah, we did all the calculations in order to determine which thickness of the bulkhead we needed to maximize the strength force of this eyeball. So all these calculations are done in the technical report. So also we take into account some reference that talked about how to joint this type of eyeballs in order to have a secure joint and to have all the strength that these eyeballs offers to us.
The presentation we are sharing on the screen shows a little bit of those finite element analysis that were done. Maybe you want to explain further on them.
Yeah, so as I explained before, with all the forces that the forces that we calculated related with the opening forces of the parachute and the shock force during ejection, we did all these analysis using ANSYS As you can see on the screen, we have a safety factor of, if I'm wrong, like 2.2 safety factor of these forces. So we are pretty sure that all these bullheads and the eyeballs and these recovery harnesses, like these quick links are rated to 25,000 newtons, and that is like, I'm going to say you like the value in labor force. So yeah, all these recovery harnesses was calculated and was determined that. Oh yeah, so these. Yeah, so these, for example, these recovery harnesses, like the quick links, are rated to 5,600 labor forces of strength, and disabled have a little bit of lower strength. That we're talking about like 5,000 labor forces, but these strengths are lower than the forces that we're expecting during the flight. So maybe if you have any questions regarding to this eyeball and the way that we are connecting to the bulkhead section.
Yes, so all of your bulkheads then are connected via screw
To the fuselage, to the airframe, yeah.
through the airframe.
Yeah, to the airframe, all these bulkheads are attached via screws. As Melissa and Diego said before, we are using 8 M6 screws. As you can see here.
And have you performed the shear analysis on those screws?
Yeah, all the shear analysis of the screws were done. If you maybe want to expand a little bit of that.
Yeah, we basically perform an analysis where the shock cord is loaded, and we insert a force into the eye bolt, and this force is transferred via the screws to the airframe. And yeah, all was checked out, and it's I think it has a safety factor of 3, but yeah, it's checked.
In addition to guarantee the holes, the iframe integrity, we are going to apply a carbon fiber reinforce to these holes inside the fuselage in the inner section.
So you said you're going to, sorry, it was a little quiet. You're applying carbon fiber reinforcement where?
In the whole sections for the fuselage, we are going to apply a carbon fiber reinforce.
The holes like on the inner side, like where you
Yeah, on the inner side.
Okay.
To guarantee the structural integrity of the fuselage.
Yeah, like you can see like the holes on there, like the inner surface, they're going to be right here. The reinforcements, sorry.
Okay.
So maybe it's clear. Maybe you have some questions regarding these ejection events, or maybe the structural analysis that we have done. All this information is located in the technical report with a little bit more of profundization on the information, but yeah.
Yeah, that technical report, it's very long, not gonna lie.
Yeah. So how long are your coupler tubes back to the body of the rocket?
So this copper tube that these two sections are not intended to separate, they are 18 centimeters long. It is 18 centimeters long, which is a little bit, it is slightly more than one caliber of the fuselage of the rocket. So it complies with ESRA requirements. And the other coupler, we have 2 in total. Well, 3 if we count the one on the nose cone, but we already talked about it. These 2 parts as Dylan said, they are intended to separate. So this part is held on with screws. And this part we have 4 shear pins. Its length it's slightly more than 2 calibers, which also complies with ESRA rules and requirements.
So why are you attaching this coupler with screws instead of epoxying?
Because right here will go this bullhead where the eyebolt goes, and where that egg shock cord will go attached to it, and it will like keep hold together this bottom section of the rocket. So it's gonna be like right here. This bullhead it goes inside of the coupler and it's attached via screws. Like
Okay, I see. So you're saying that that goes inside of the coupler and then the screws go through the body tubes, through the coupler to that bulkhead.
That is correct.
Okay. Okay.
They're international, Sierra. I bet they have to take it apart. They can't do it.
Yeah.
Actually, like this section of the rocket is going to be like in a pretty big box, so we couldn't do it any longer.
Mm-hmm. Yeah, and you said your rocket is going to be transported just in separate suitcases on your way here?
Yes. We'll have several suitcases with different parts of the rocket, and we are also planning to manufacture some boxes to keep them secure and to avoid like any damage to it in general.
Yeah, so how are you going about acquiring your motor? Have you acquired it somewhere in America, shipped it already, or how are you managing that?
We bought the motor with Wildman Rocketry, so we will have them like shipped to the competition. We couldn't like bring it here as it will be like too expensive, and also we cannot transport like explosives on our airplanes, so that's another thing.
Great. And then anything else you need? Like, are you bringing e-matches? What type are you using?
And we're planning on buying.
No, related with the images and all these like energetics, we are planning to buy all these energetics in the US. We already have done the research of where we can buy these energetics such as like the black powder, the CO2 cartridge, and the images. The images that currently we are working on and are the same that we are planning to buy in US are some images used like in the pyrotechnic topic. So yeah, all these energetics we are planning to buy them in US. We already have the locations and the stores that have it.
Okay, great. And then how is your motor retained in your rocket?
So here's a little bit of how this how the system is. So this I'm going to take like this screws up. Well, this is our transmission cross plate. This is right now 3D printed, but the final one is not going to be 3D printed. It's going to be in aluminum 6061 T6. Just that we don't have it yet, but we 3D printed this so you can see like more clear how this system will go. So we have this steel C-shaped hooks where the motor will rest at, and that's how we will retain the motor. We plan on carrying like several of these hooks with different dimensions, different lengths of these, different heights, so we can like choose the one that fits best in the motor. I'm going to take this off so you can see like how is the assembly.
Okay, and did you make these hooks or purchase them?
Oh no, we made it just like with plates of steel. Like we folded them and then like do a thermal treatment to make them more more resistant. Yeah, like harder.
Yes. So have you done any analysis on the thrust around this area?
Yes, we did. Actually, as you can see on the presentation of the screen, we did several finite element analysis to check that we have the enough safety factor for this. Yeah, you can see that on screen. We also did that analysis to the C-shaped hooks. So basically, the thrust disc, I'm sorry, is going to be like this, as you can see, a plate with 3 holes for the screws to retain them on. But it's going to be aluminum, the final one. We also will have this plate. This one is in wood, but the final one will also be in aluminum. This will go like epoxied and with some screws to avoid that, so that it can't mechanically move. And yeah, that's basically how we plan on putting on like this retaining system, and also the thrust transmission system.
Okay. And
Also, you can see, I'm sorry.
I was just going to ask, what are the size of those screws?
The final ones are going to be M6.
M6. Okay. And you have those, are they epoxied on the other side of the plate?
Yeah, no, like we will put them like this way with these nuts, like hold them really tight, put some nut locker, like some Loctite, and then we can just like put the thrust disc in, the C-shaped hooks, and put some nuts to keep them together.
And you were saying this plate is being epoxied?
Yeah, like
Is the
one
thrust
that
plate being epoxied?
This won't, so we can like take it on and off to
Okay.
put an on and off like the motor. This will be held by, that's like, basically we will do exactly this. Put the C-shaped hooks and put a couple nuts on this.
Is that it's on upside down right now? You can see there's a lip, right? That thrust ring has a lip on it.
I'm sorry.
Yeah.
Yeah, like we have the lip to like center the transmission
Okay,
ring
good.
on the fuselage.
Okay.
Okay, I want to say that the reason that you can't see the final thrust ring is because we had a little problem with our machining company, so we decided to print a 3D
mock-up.
A 3D mock-up, yeah.
Mm-hmm.
So you're having trouble with the machine shop right now?
The thing is that there was like a confusion, and like they did another piece, so we are like expecting to buy the material and to send it to be machined again. Like,
yeah, for this
Okay.
reason you
Well,
can
you only
see
have a couple weeks, right?
Yeah.
yeah, we have all it sorted out. Like nothing to to worry about. It will be.
All right.
It will get done.
All right.
So you have your payload frame is being machined.
Yeah.
Your thrust plate is being machined. Is there anything else you're waiting on to complete machining?
Well, like to machine, like that will be like it for the rocket. That will be like the last thing that it's missing that we don't have like right now.
Okay. And do you have an estimate when that will be complete?
We expect it to not be later than next week.
Okay.
Like
okay.
the later.
Okay.
We really do have to buy again the material, and the company is in this moment ready to machine our component.
In a day it gets ready, so it can get done in time with no problem.
Okay. And then could you zoom in on your fins and tell me a bit about what you did there?
Well, first of all, we haven't sanded them yet, so they're like kind of ugly. So sorry for that. So our fins, we did them on compression molding, fiberglass compression molding with directional carbon fiber reinforcements. This one that I have right here, it's one of the like the first fin that we made that didn't like exactly turn out like geometrically how we wanted, so that's why it is not glued on the fin but on the rocket, but you can see it. On the presentation you can see the photo of the 4 fins before glue them on the fuselage. And yeah, we glue them and aligned aligned them using a laser level. And we did that before putting the epoxy adhesive and also after putting the epoxy adhesive to ensure that the alignment were correct. We did some fillets also on them to secure them more like structurally and for drag reduction.
And are these fins through the wall or
no, they are
okay.
surface mounted.
Okay, but you're doing tip to tip fiberglass?
Yep, that's exactly what we did here.
Or
Carbon fiber.
fiber.
Yeah, carbon fiber tip to tip reinforcement, which you can see like here on camera. We did three layers.
Okay.
3 layers of what weight?
That 200 grams. I don't know how much that is in ounces.
Grams. Well, is it, they call it like 3K or 6K or 12K?
3K.
3K? All right.
Yeah.
Okay. And
yeah.
could I see your fillets again?
These are like the fillets. We did them of 21 millimeters radius, and we use the same aeronautic grade epoxy adhesive that we show you that we will be gluing the nose cone metal tip with.
Okay. And then when you kind of roughhouse it, does it feel firm?
Yeah. Yeah, it does really feel very firm.
Because the safety reviewers are definitely going to tug on them. So make sure you're comfortable with that.
Yeah, like actually, it's like I'm really doing force on them and they're like, pretty well. Yeah, as you can see.
Back when because I was a former student competitor myself, back when I was on my team, my alumni told me to be prepared for the safety reviewers to like jump on your fins, like they'll really test them out. So
like we're pretty confident that these fins will endure the mistreat that they will receive.
That's good. That's good.
I think that the only thing that we're missing to review are like the centering rings. Will be like these. They are MDF with fiberglass reinforcements. You can see them on the inside of the fuselage right now through camera. We have 3 of them.
Okay. And then, so I see the centering rings. Do you have a tube that your motor will slide into?
No, just the centering rings. That's the reason we have more than 1 or 2 of them.
Okay.
Yeah, I don't know what else would you like for us to show I don't know.
Where are you going to put the rail buttons? Where's the rail button mounts?
Oh, the rail buttons. We didn't mark them, but they're going to be about this height, about 6 centimeters from the edge, and up here, about 91 centimeters from the edge of the rocket.
Are you going to put another? Are you going to put another hole into that bulkhead and screw the thing into the bulkhead?
Into the bulkhead, no, like into the fuselage and the copper, like will.
You know what I'm saying though, right?
Oh, yeah. I'm sorry. I was saying something that was wrong. Like one of the rail buttons is going to be right there, and the other one ends up right here. I'm sorry, my bad. It's going to go through the fuselage and yeah, not the copper, like the fuselage. That's why you can see that the piston. Yeah, it won't touch the copper. That's why you can see like the piston has like.
Well, that bulkhead, that big aluminum bulkhead you have right there.
Yeah.
That'd be a really good spot to put a rail button in between 2 of those holes.
Yeah, you just have to make sure you use the same alignment every time.
Yeah, like we don't really like touch more these bulkheads. Just like they were CNC machines, so like we don't want to mess up with them. But we will reinforce the the spots where we put the rail buttons with fiberglass layers.
Well, you need a nut.
Yeah, we were buying commercial rail buttons.
Okay. Did you look, are they coming with the little nuts on the backside?
Yes, sir.
Okay.
Okay.
And you're buying those in the US, right?
That is correct. We are buying them from Wellman Rocketry as well.
Okay.
Okay. And then a few questions, just kind of general calculation questions. What is your current fin flutter?
It's more than double the maximum speed of the rocket. It's 726 meters per second, and which is could someone please put that in feet per second?
Well, where's your fin, Melissa? Because you're not using flat fins, right?
No, we're not. We're using airfoil
Yeah.
ones. So what
Yeah.
we did for the calculations was to put
Estimate.
an average thickness.
Okay. Yeah.
Good. Yeah.
Yeah, we have used a symmetric airfoil, a NACA,
Right.
a NACA 16006
See-
to the objective of
Yeah, I would
reduce.
I would annotate that on your fin flutter there. You know, number one, you're using an airfoil, so it's not a flat surface. And then number two, in order to because you can't use this equation with something that has a multi-dimension, right? This equation require or assumes a flat surface throughout the width of the fin. And so you need to annotate here that you use the average thickness for this particular calculation simply because you have an airfoil and therefore this equation can't be used.
Yeah, we put that on the technical report. We really kept that in mind when doing the flutter calculations. But yeah, it was a mistake to not put it there on the presentation. But here, like
Yeah, it doesn't have to be like a long paragraph. It just has to be, a couple little notes on there.
yeah, we on the technical report, like we have them in yeah. So all clear out for that aspect.
Great. And then what is your effective rail length?
It's 3.86. Oh, that's 3.86 meters. I don't know how much that in feet. 12.6 feet. That's our effective rail length.
12.6 feet.
Yeah.
Okay.
So when you did your simulation, what length did you use for a rail to get your rail departure speed?
We did it with the one that provides ESRA, but we also did the open rocket simulations with the effective rail lengths. So we are all good on the rail departure speed.
Gotcha. So yeah, their rail departure speed is like a real when the first rail button comes out of the rail.
Yeah, we really kept that in mind when doing the simulations.
Yeah, so all of these numbers that you've given me have been with your effective rail length then?
Yes.
Okay. 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 Well, I have some good news for you guys. Oh wait, one more question. We talked about rail buttons. What type of rail buttons are you using?
Like the typical ones that are like rounded.
Yeah, standard.
Yeah, standard rail buttons.
Like the size.
Oh, the same size of the rail guide. Like I don't remember if it's on metric or on imperial, but it's like 10 or 15.
Well, those are the two different types. So which one is it?
Yeah, 15. Yeah, we
Okay,
checked that
good.
it was the compatible with the railguide.
Okay, good. Very good.
Perfect
Okay.
right button for our selected guide,
Yeah.
the ESRA guide. So
Okay, so what quick payload question, what is the weight of your payload?
It's a maximum of 4 kilograms.
But do you have like the estimate from your model?
3 point. We are at 3.2 kilograms, but we said like a maximum of 4 kilograms, saying that like we don't have like the finished structure yet, but so we did the calculations for a payload of 4 kilograms.
Okay, and where is it in the rocket? I don't know if we ever really looked at that, where you're putting it.
Sorry, C2 what? Oh, okay.
Where the payload is.
In general terms, the payload is going to be located like inside of this coupler tube. We designed this structure in order to maintain the payload in its location during the ascent, right? So this structure, the final structure is going to be 3D printed in ASA material reinforced with fiberglass. And in order to maintain this structure into the coupler tube, we designed it like these small radial like radial attachment points. And we also already did the FEA analysis, the finite element analysis for these elements in order to determine and establish that this is going to resist the weight of the payload during the initial acceleration forces. As you can see in the presentation, next. And back there. And in the technical report, we have all this FEA analysis. So yeah, we did all this analysis. This payload is going to be located inside of this coupler tube, like at this point. And we designed
I
the
can't see
ejection.
your screen anymore, like your video. Okay, thank you.
Oh, and this payload is going to be located like at this point on the coupler tube, and the ejection piston is going to be located on the top of it. We designed this like we call it like the bucket piston, because it works like the piston to the ejection and also like an additional structure to maintain this CubeSat in the same position during the flight. So yeah, the CubeSat is going to be like in this position, and this bucket piston is going to be located right there. Yeah, and also this bucket piston has like this rail, like this slot, in order to allow the pass of the nut of the rail bottom. Also, we'd already done all the finite element analysis using a dynamic analysis of impact of this piston and the main piston that you can see right here. These pistons are 3D printed with ASA reinforced with fiberglass on all of the structure. Also, these pistons have like a sealant component that is a tire, a used tire of a motorbike that we use like to seal the ejection gases. This sealant method also is used on the bulkhead of ejections. As you can see, all this pneumatic, all this tire were from a motorbike, and help us to maintain like a seal compartment during the ejection events.
Okay, so where in the rocket is the payload then?
Exactly
Like at what point in the rocket?
In this position, like there. Yeah.
Down towards the motor?
Yeah. This
Okay,
is the
and
motor
then-
section, and this is the recovery bulkhead, and the payload is going to be like there. Yeah.
Okay, so it's motor, payload, Then there's
And
the parachute on the other side, and that's the drogue parachute.
drogue parachute, yeah, correct.
And then as you go up, you've got the avionics bay.
Exactly. We have the drogue parachute. We have the ejection bulkhead. All this is the avionics bay. Here we have the another ejection bulkhead. Here we have our main piston, our main parachute, and yeah, the nose cone.
So how heavy is your avionics bay with your ejection systems?
The avionics bay, sorry. The avionics bay is approximately 2 pounds. And the ejection bulkheads.
I can't hear you very well.
Can you hear me now?
Yeah, I can hear you better.
Okay, I'm sorry. It's about half a pound each. There are 2 pounds each ejection bulkhead, like complete. And this is also 2 pounds. So like 6 pounds in total, all these, the 2 ejection bulkheads and the avionics bay.
Okay, and then in the nose cone, you just have the parachute?
Yes, that is correct.
Okay. So you definitely you have a bit more of an unconventional setup because obviously your payload experiment is it's unique, you know, you're trying to analyze the atmosphere, obviously. So typically sort of the weight requirement we have for the payloads is to encourage you to have a good stability to balance out your large motor. So I was just kind of trying to see where your stability is coming from. So it seems like your avionics bay has most of the weight towards the front of the rocket, but it's not quite as high in the rocket as I would expect.
Well, given that we also have a very robust metal nose tip,
Yeah,
like
yeah.
it also like adds weight to this upper front part of the rocket. Also, like the nose cone, it's a little bit heavier than we expected, so actually that also helped us with that stability.
Okay, and you've updated, or are you planning to update your open rocket with your actual weights once you have everything?
I'm going to let David explain that to you.
In every stage of the design process, we are currently every week updating the weights of the rocket.
Okay,
So
good.
right now, the simulation that it's in the presentation, you can see, it's currently with these weights, exactly as we have them currently.
Okay, great.
And regarding your question, another main source of stability is our main parachute, because it is just at the nose cone. And
How much does it weigh?
this one, it's around 1.9 kilograms, which is almost 4 pounds.
Yeah.
Considering also the deployment bag weight.
Yeah, I got you.
Okay.
Regarding parachutes, there is something I would like to add. And it's that these coach parachutes are actually planned to be used in case of a backup, because our main objective is to fly with SRAT parachutes, just because the encouragement of ESRA to use SRAT components. Currently, out of the 3 parachutes, we have developed the pilot chute only. We are currently manufacturing the drogue and main parachute, but they are still not ready. We actually expect that these SRAT parachutes are more sophisticated than the CUTS parachutes, even when considering that these are pretty good parachutes. We really expect to design better ones. And just as an example, the pilot chute, it's a cross geometry. It is just like, a square. And all 3 parachutes will have the same geometry. The drop one is very similar to this one with just 4 inner gores, and the main one has 16 in total. And that's our main objective. I think that it is relevant that you know about them.
Okay.
And I gave you, just to make a little note, I make you at the beginning of the meeting, some values of diameter and descent rates for the CUTS parachutes. For the SRAT parachutes, we are still meeting the requirements. So for the case of the drop SRAT parachute, we are obtaining a minimum descent rate of 25.16 meters per second. And it is a parachute with approximately 1 meter in diameter. The descent rate in feet per second is equivalent to 82.5 feet per second. And that's regarding the SRAT drop parachute. It is already designed to withstand high forces, such as the rest of the rocket, and the same case for the main parachute. It has in total a diameter of approximately 5 meters and a descent rate of 4.5 meters per second. As you can see, both main parachutes have a similar descent rate. Because of the requirement of the payload, we have to descend at a slow velocity in the final phase. And that's it.
Okay, great. So now I just have some final questions, not really technical anymore, so you can kind of relax a bit. First off, I already asked you about painting the rocket, but I just want to make sure you guys are going to mark your payload with your team name, number, and frequency as well.
Yes,
Okay,
we
good.
can definitely do that.
Great,
And
great.
we also expect to stamp or make a mark over the parachutes just to make an identification pattern.
Cool.
Well, you need
cool.
to put your team number on your rocket.
Yeah, we
Yes.
can do that too.
Yes. Okay, great. And then have you been to competition before? Any of you?
Specifically, IREC competition, no, but some team members have previous experience in competitions.
Yeah, like we have participated in other competitions. For example, in 2023, we went to the Latin American Space Challenge in Brazil. So we have kind of some experience with competitions.
Okay, great. Have any of you ever been to the United States before?
Some of us, for some others, are the first time. We have like a little bit of everything.
Okay, cool, cool. So, do you have an idea of what you need to wear to competition?
Yes.
Okay.
Yeah, we have like the hats. We have we're planning very well like the uniform, like with boots, some long sleeves, some fresh t-shirts, also like the sun hats. We have like everything, keeping everything in mind. Also like the long pants, preferably cargo in order to keep like things in handy reach. So yeah, we're taking that into account.
Great, great. And then you guys are aware that you have to bring your own chairs, right? Are you bringing chairs with you?
Yeah, like probably we're going to bring like some, ¿cómo se dice esa vaina? Yeah, like maybe some extendable chairs and also like some like fabric to put on the ground and like sit on and like blankets. That's the word. Some blankets also.
Yes, yes. And then, you've got to make sure you're hydrated, you have enough snacks, have a lot of electrolytes. I mean, honestly, you just have to buy like cases and cases of water every day.
Yeah,
So,
something that we're planning is like we obviously gotta rent cars, so we have like a big bags of water to like on each car, so like
Yeah.
we can keep drinking water throughout the day.
And you're planning to bring 26 people to competition, correct?
That is correct. We are a lot.
Assuming visas work out, right?
Yeah,
So,
we're 26 students.
do you know how the visa status is right now?
Right now, we all have visas.
Okay, so you're all good, all 26?
Yeah, all 26.
Okay, great. Good job. Good job. I know that can't be easy. So, great job. Be prepared. It's a lot of work managing 26 students, especially are you bringing an advisor with you or will it just be you?
We'll be bringing a couple of mentors and also some parents tagged along the trip, so they'll also be there as spectators.
Okay, will they be staying with you or staying separately?
Oh, they will be staying with us. We are like all staying on the same hotels and stuff.
Cool, cool. So you guys are getting hotels?
Yeah, like on the first week, we arrive to the United States on June 3rd. So from the 3rd to the 8th, we will be staying like some part of the group at an Airbnb and the other part at a hotel. And from the 8th to the 16th, we will be staying all in the same hotel.
Okay, great. So you're arriving early then. Are you doing anything beforehand? Are you going anywhere or working on the rocket before?
Well, like something that we have learned is that we need to have time ahead to prepare things in case like anything happens during the trip. We hope really that nothing happens, but like we have time like to prepare, check that everything is all right. Also, given that we bought the motor and we have to do the grain bounding, we have to like arrive a little bit earlier. We're still pending for One Man Rocketry to tell us how the process will be. I don't know if maybe you have some info about it, like the teams that buy Coats motors, like if they are uh, giving them out like on the first day of the competition, or if like they can do it days earlier. I don't know if maybe you have some information about it.
I think you would get your motor on the first launch day, but I'm not 100% certain. But I know that they have a big booth. Wildman has a booth where they have their big truck full of motors that they hand out to the teams that ordered them.
Okay.
So, Melissa, yours have you looked at the instructions? Yours requires grain bonding?
I'm sorry, could you please repeat again?
Have you looked at the motor that you've chosen, the
Yeah.
motor you've selected, and the one you've ordered from Wildman? Have you looked at the assembly instructions and
Yes.
does it indicate that you have to do grain bonding?
Yeah, it does indicate that we have to do a
Okay.
grain bonding. We have like
Good.
the PDF assembly instructions, and we will be contacting. I mean, like we contacted One Man Rocketry about the process like 1 month ago. They didn't have like that sorted out yet. We plan on contacting them again this week, so we can plan that grain bonding ahead of time.
Yeah, it typically, at least let me just say, in the past, what I have seen is it's dependent upon when the vendor shows up, but the vendors usually show up while out at like the launch site while you guys are still in the conference hall. And if you need to do grain bonding, then you might need to send somebody out to pick up the motor so that you can do the grain, because that's a 24-hour process. And there's other motors that require that. So
Yeah, I'll check about that just to make sure that you will be allowed to pick it up from the launch site early. But I'll get back to you about that.
yeah, as long
Thank
as you
you so
don't bring
much.
it into the conference center. Do not bring your motor
Okay.
in the conference center.
Yeah.
Yeah, we'll take that in mind. We don't want explosives in the convention center. So
Yeah, people will
And-
get very grumpy if you do that.
Yeah, only load it up when you're ready to go to your
Yep.
final flight readiness review.
Yeah.
Which is out at the launch site, not
Yes.
in the building.
Yes.
Yep. Yeah. We'll take that.
And of course, your flyer of record needs to be with you, needs to see
Obviously.
what you do with your motor. Is anyone on your team certified?
No, Given that in Colombia there are no AAA prefectures, it's
Yeah.
not that easy to get the certification.
Yeah, yeah.
So Wildman's not going to hand you the motor. He's only going to hand it to me.
Yeah, we will reach out to Wellman, and depending on what they answer to us, we will definitely tell you how the process will go, and to check that out with you to see which is the best way to assemble to do the grain bounding and the stuff.
Yeah, we're going to do it not the way the instructions say.
Okay, you're the one that are certified. We attend to your instructions.
I use silicone instead of the glue. Just it works really well and it
Okay.
doesn't cause other problems.
Okay, perfect. We will follow your instructions when the time comes.
Okay, and then where is your team staying? What city? And you said you're staying in hotels for most of the time?
Yeah, so the week, from 3rd to 8th that we arrive, we are staying at Midland, but then the rest of the days we are staying at Odessa.
Odessa's only a little closer.
Yeah,
Yeah.
that's why we chose to stay there, like the days of the competition.
Okay.
Yes, so just, I guess a little inside scoop from Uprange. We do plan to open the gates each day at 5 a.m. and start launches a couple hours after that as soon as we can. Do you know when you're planning to launch? Are you trying to launch early morning first day, or you're just kind of waiting to see?
We are planning to be able to launch like the first day early. That's why we are coming to the United States like also early to be able to prepare like everything and do like also travel as soon as possible.
Yeah, okay. Definitely coordinate with Wildman then, and definitely try to launch as early as you can. Earlier in the day, the better, the lower the winds. So,
yeah.
So what you guys were the ninth team to submit your application, right?
Yeah, like we were early on the application.
They nagged me, Sierra. When
yes,
can we do it, Chris? When can we do it? I was like, I don't know. I have to wait.
I've been very impressed with your team this whole time. I mean, you should know that not all teams do what you are doing. Like you have all documented very thoroughly and very well. You present yourselves very well in your reports and your presentations. It looks nice. You have a lot of good information. You're kind of going above and beyond in what you're simulating and calculating and turning in for progress reports. So you should be very proud of yourself. You're doing a great job.
Thank you so much. We are indeed very proud of the work we have done. We really have put our hearts and our lives and our sleep and everything into it.
Yeah. It's evident. It's evident.
Thank you so much.
Yes. Okay. So who is here for this? Is this most of your team that's here, or leadership?
It's mostly leadership, but also like other team members. There's still a lot of people missing. We are a really big group, like some of the teammates. But yeah, and also some other ones are like on the Zoom call, but not here in person. Yeah, some others
I'm gonna ask a weird question, Melissa.
Okay, go on.
So of the people that I can see in the video, are all of those people coming, or is there anyone in your room right now that's not coming?
I think only one person is not coming.
Aww.
Only he's not, and her like, but the rest like we are all going to the United States.
All right, cool.
Well, maybe next year.
Yeah, hopefully so. Oh, and also the other teammate that is like on the window.
Okay, great. Well, thank you guys so much. Just remember to be safe. And, you know, I'm not worried about how you will behave. I think you guys seem like a very good group of people. But you know, you represent competition when you attend, so you know, just be polite, make good choices, don't do anything dangerous if at all
Nope.
possible. So
No bar fights, Melissa. Don't
yeah,
start any bar
Okay.
fights. Get thrown in jail.
yeah,
No, we don't want to end up in jail.
All right.
Actually, most of the teammates are under 21, so they cannot drink either. So no
Yeah.
bar fights for them.
All right.
Okay, great. Thank you guys so much.
Thanks to you, Sierra.
Thank you, Sierra.
Oh, make sure to send this to general.info@ESRA Rocket, remember?
Yeah, as soon as we like download the video, we will send it to the general. I have a question. Like, if the video is like the file is too big, like we send like a compressed folder or like just a Google Drive link. Like, what do
Yeah,
we?
you should be able to send a Google Drive link. Just make sure that he has access to it.
Okay, perfect.
Okay.
Thank you so much.
Great. Thank you guys. Bye.
Bye bye.
See you guys.
Bye, Chris. Thank you so much.
You're welcome.